Hi, you guys. Today I have with me problem 5.11 from Young and Freedman's University Physics textbook. Like I mentioned in one of my earlier videos, this is another space-themed question, my personal favorite from a past era of my life that was really meaningful to me. So I'm always down for a good space problem. All right. So this problem is called Stay Awake. But before we get started on this problem, please don't forget to like and subscribe and share my videos if you find them helpful. Thank you so much. Okay. An astronaut is inside a 2.25 times 10 to the 6 kilogram rocket that is blasting off vertically from the launch pad. You want this rocket to reach the speed of sound, 331 meters per second, as quickly as possible, but astronauts are in danger of blacking out at an acceleration greater than 4g, where g just means gravity, acceleration due to gravity. Okay. What is the maximum initial thrust this rocket's engine can have, but just barely avoid blackout? Start with a free body diagram of the rocket. B, what force in terms of the astronaut's weight, W, does the rocket exert on her? Start with a free body diagram of the astronaut. C, what is the shortest time it can take the rocket to reach the speed of sound? All right, a super fun question. So let's start off with our diagram. Okay, cool. Sorry. I paused there for a second because I thought I was muted and I'd have to refilm that. Okay. So, rocket, and it's going to be something like this. That just looks so weird and creepy. Okay, let me try that again. Or I think, hmm, now it just looks like some weird spider rocket hybrid. Okay, whatever, really doesn't matter. Maybe I can just add other features to make this look like a rocket. I think I've done this in like that other video I posted. So there we go. And then, oh, obviously we can add like fire. Cool. And we'll add a window too. And the window will be blue. Cool. Okay, there we go. Now that looks a lot more like a rocket. Super fun. Okay. So it's blasting off from vertically from a launch pad. Okay, so let's just set up our coordinate system. Let's go ahead and this is positive y, and this is negative y. All right? Okay. And the masses, we can write that down on our knowns later. Speed of sound, write that down on our knowns later. And then acceleration, write that down on our knowns later. Okay, so this is essentially it. Let's start with part A. But before we do that, we want to write down our knowns. Okay, so our knowns. Mass of the rocket, 2.25 times 10 to the 6 kilograms. Okay, and then speed of sound, or actually I should do VS because that's, okay. VS, and that's equal to 331 meters per second. And then we have acceleration, and that's 4g. Okay, cool. That's all the information that's provided in the question. Okay, so A, what is the maximum initial thrust this rocket's engine can have, but just barely avoid blackout? So let's start off with the diagram, force body diagram of the rocket. What are the forces that are acting on this rocket? Well, we have Fg, right? Because we're going to assume that this rocket is taking off from Earth. And we also have thrust, right? So Ft, thrust. Cool. That's it. All right. So if we want to get the maximum initial thrust this rocket's engine can have, but barely avoid blackout, what we want to do first is we want to start with so we want to find out the maximum FT, like max, is what. So let's start off with a forces statement to describe the forces in acting on this system. So Fy, because that's the only direction the forces are acting, right? Because it's blasting off vertically. Fy, and we said that up is positive, down is negative. So all we have is Ft max, right? Minus Fg. And what's that equal to? That is equal to mass times acceleration. Okay, so we're solving for Ft. So let's isolate for that. Ft max is equal to mass times acceleration plus Fg, right? Force due to gravity. And what is m? M is the mass of the rocket. What is A in this system? So A, it says that in our problem, it says that astronauts are in danger of blacking out at an acceleration greater than 4g. And we are barely avoiding blackout. So we're looking at the limit. So the limit is the acceleration, which is acceleration at 4g, right? So Ft max is equal to 2.25 times 10 to the 6 times 4, 9.84g plus Fg, which is, again, 2.25 times 10 to the 6 times 9.8, right? Well, okay, this is one way to write it, but actually a better way, I should have done this way. And this is essentially just MA plus MG, right? So MA plus MG. And we can just do M plus A plus G because we're just collecting like terms, right? So we collected the M, we factored out the M, so we just have A plus G. So Ft max is just equal to M A plus G, which is 2.25, 10 to the 6, right? Times acceleration, which is 4g plus g, and that's just 5g, right? And this makes sense because this is the exact same thing, right? These are equal to each other. So Ft max is equal to 2.25, 10 to the 6 times 5g, which is 5 times 9.8. And that is equal to plugging it into my calculator. I'm getting 1.10 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. 8, and then newtons, right? So that's what we have for Ft max. Okay. All right, so that's part A, and we can actually write that down over here, I guess. So Ft max is equal to 1.10 times 10 to the 8 newtons. Okay. And now we're going to solve for B, right? So what is B? B says what force in terms of the astronaut's weight W. So actually that's something we should write down in our notes as well. The astronaut's weight is just W. The astronaut's weight. So weight of astronaut is just W. Okay. Okay. Does the rocket exert on her? Okay, so this is an interesting one. Okay. So let's start with the force body diagram of the astronaut. And let's do that in pink. So FG, obviously, because she's going to be experiencing force of gravity, right? And then we also have, because she's like, let's say, like, she's sitting on a surface or she's standing on a surface during takeoff, at least, right? That means that she's going to be experiencing a normal force, right? So, like, let's say this is like part of the rocket and this is her. So FG, she's going to be experiencing force FG. And then because she's on a surface, also FN, because the rocket is going to be exerting a force on her as well. Or like the floor of the rocket or whatever, right? Okay, so FN. All right, so B, or let's do it in purple actually. It'll be a little prettier that way. So the summation of forces in the y direction, right? That's what we're summing up for the astronaut. But what is the total summation of forces? Well, it's going to be like F is mass times acceleration, right? And what is mass times acceleration? It's going to be her mass, right? Times the acceleration of the rocket because she's accelerating with the rocket if she's inside the rocket. And what did we say was the acceleration of the rocket? 4g. So m times 4g is the net force in the y direction. All right. But what are the summation of forces that she's experiencing? Like, yes, this is the net force, but what are the summation of forces? Fn, because that's in the upwards direction, minus Fg, right? Because that's downwards. And that, of course, is equal to 4mg. And mg, we know, is just equal to W. That's weight, right? So Fn minus Fg is equal to 4W. So, and we know that this is equal, Fg is equal to weight is equal to mg. So Fn minus W is equal to 4W. And that means that if we want to isolate for Fn, because we're looking for the force that the rocket exerts on her, which is Fn, that's just 4W plus W, and that is 5W. So that is the force that the rocket exerts on the astronaut, right? Okay. Now, C, what is the shortest time it can take the rocket to reach the speed of sound? So maybe we can just write that down in purple here so that we have that for our own reference. All right, so C, let's do that in orange. Why not? What is the shortest time? Okay, TS for shortest time. It can take the rocket to reach the speed of sound. Okay, so maybe we can go ahead and write down our knowns for this portion, right? Because we haven't been really thinking about yes, we've extracted all the knowns from the problem over here, but in this specific situation, right? So shortest time it can take the rocket to reach the speed of sound. So let's pull here. To reach the speed of sound implies that there's an initial speed and then there's a final speed, right? And the initial speed has to be zero because we're taking off from nothing, obviously, right? And then the final speed is the speed of sound. So 331 meters per second, right? We also have the acceleration because we know that this is the limit for acceleration before the astronaut like knocks out or like blacks out. So acceleration is equal to 4g, and we're just solving for s. So now we start with, or we ended up with a basic kinematics problem, right? And we are solving for t. So we can use this equation. A is equal to, we can just use the equation for acceleration. So vf minus vi over t, where we're solving for t. So t, rearrange. Yeah, so vf, one sec. I was about to rearrange it wrong. So t vf minus vi over a, right? And we're just going to plug in our numbers. So vf is 331 minus vi, which is 0, over acceleration, which is 4g, but 4 times 9.8. And what's that equal to? 331 divided by 4 divided by 9.8. And that is 8.44 seconds, right? That's what we got. So that is the shortest time it can take the rocket to reach the speed of sound. There we have it. We've solved problem 5.11 from Young and Freedman's University Physics textbook. I hope that was helpful. If it was, again, please don't forget to like and subscribe. Thank you so much for watching and see you next time.